Hi everybody, welcome to video lecture number 5, the electromagnetic spectrum. The light we see on Earth is a type of electromagnetic radiation. What is radiation? It's energy that spreads out as it travels. Electromagnetic radiation is energy made up of special particles called photons. This energy travels faster than anything else known in the universe, at about 3 million meters per second, or the speed of light. There are many different types of electromagnetic radiation, including the light that we can detect with our eyes. But all types of radiation travel as waves. So to understand the different types of radiation, we have to start by learning the structure of waves. Go ahead and pause the video and write the essential question in your notes. Every wave, whether it's caused by skipping a rock across the water or by plucking a guitar string, has a certain structure. What is a wave? A wave is the transmission of energy through a medium, like air or water, or the transmission of energy through empty space. Waves hitting the beach transmit energy. Ultraviolet rays transmit energy from the sun, and they'll burn your skin if you aren't wearing sunblock. Whatever type of wave we're talking about, it's a transmission of energy. The amount of energy delivered depends on how many waves are transmitted. And when we're talking about light waves, that's determined by two things that are directly related to each other: wavelength and frequency. Look at this diagram of the structure of a wave. Every wave has crests, the highest points, and troughs, the lowest points. The distance from crest to crest, or from trough to trough, is the same and is called a wavelength. All light, or electromagnetic radiation, travels at the speed of light, but different types of light have different wavelengths. In addition to wavelength, electromagnetic waves can be measured by frequency. Frequency refers to the number of waves that pass a given point in a given period of time, usually 1 second. Electromagnetic waves that have lower frequencies have longer wavelengths. In other words, fewer waves pass a given point each second because the wavelength is longer. Electromagnetic waves with shorter wavelengths have higher frequencies, which means more waves pass a given point each second. More waves means more energy being delivered. The shorter the wavelength of light, the higher its frequency and the more energy it delivers. And the longer the wavelength, the lower its frequency and the lower the energy delivered. Our eyes are really fascinating structures. Visible light, or white light, the light that we can see, is a range of electromagnetic waves that we see with our eyes. We perceive different wavelengths of light as different colors. The color red is light that has the longest wavelength that we can see, at a very small distance of 665 nanometers, or billionths of a meter. It has the lowest frequency and delivers the least amount of energy. As wavelengths get shorter, we move across all of the colors of the rainbow. You've probably heard the acronym ROY-G-BIV. It helps you get the colors in the right order of increasing wavelength: red, orange, yellow, green, blue, indigo, and violet. Violet, or purple light, has the shortest wavelength detectable by our eyes, at around 400 nanometers. It has the highest frequency, and therefore it delivers the most energy of all the colors we can see. Do the order of these colors remind you of something we've recently studied? Think of the HR diagrams. Any patterns? More on that in class. The light that we can see is just a small portion of the electromagnetic spectrum. The wavelengths get much longer and much shorter than we can detect with our eyes. Below visible light, you have infrared radiation. The prefix infra means below or under. So infrared means below the color red. We can't see this type of electromagnetic radiation, although some animals like vipers can, but we do feel it as heat. As the wavelengths of electromagnetic radiation get longer, we move down to microwaves and finally radio waves. The wavelength of visible light is measured in billionths of a meter, or nanometers, but a radio wave has a wavelength of up to 3 kilometers. That's about 1 mile. Radio waves have very long wavelengths, which gives them very low frequencies, which means that they are very low energy. The device you're using to view this video, your cell phone, your wireless router, and of course your radio, all transmit radio waves. They're all around us, but they don't hurt us because they don't transmit lots of energy. If you move up beyond the visible portion of the electromagnetic spectrum, however, you encounter plenty of harmful radiation. Ultraviolet light can't be seen, but it will burn your skin if you don't put sunblock on at the beach. X-rays are great for imaging bones, but there's a reason the dentist puts that heavy protective vest on and then steps behind a screen before taking an X-ray image. Gamma rays have wavelengths that are so short and their frequencies are so high that they deliver enough energy to kill cancer cells, or any cells for that matter. Most comic book heroes start their stories with some sort of exposure to gamma rays. Even though we can only see a tiny portion of the full electromagnetic spectrum, that doesn't mean that the rest of the spectrum is a complete mystery. We use different wavelengths of radiation in all sorts of technologies, and to study space more closely. Most people think of telescopes in a pretty limited way. They don't just make things that are far away look closer. They reveal the invisible, if they're detecting electromagnetic radiation that's not in the wavelength range of visible light. Astronomers use telescopes to detect any wavelength of radiation, revealing some pretty awesome stuff, like radio waves here being pulled into black holes, supernovas emitting powerful gamma rays, or mapping galaxy radiation signatures to determine their shapes. The full electromagnetic spectrum, along with visible light, allow us to better understand the formation of stars and galaxies, what black holes are, whether there are habitable planets besides the Earth, and what our universe is like. It turns out, it's a pretty cool place. I'll see you next time.